Okay, everyone, assalamu alaikum and hello. Let's begin and start doing some questions on Newton's second law of motion. We started this topic in our last session. We discussed the concepts. What was this about? Basically, when you have a set of forces acting on an object and there's some resultant force because of those forces, that resultant force makes an object move, right? How do you find the acceleration of that object because of that resultant force? We use this rule, this law called Newton's second law of motion. And that looks like this: resultant force equals mass into acceleration, forward force minus the backward force, that equals mass into acceleration. When you have connected objects like this, where you have one object on one end and another object on the other end, and they are connected by a string or by some other object or by some other object. Um, how do we find the tension in the string, and how do you find the acceleration of the blocks? We just apply Newton's second law of motion separately to each of those objects, right? So we apply Newton's second law of motion to A separately and to B separately, and that helps us find acceleration and tension, right? So we looked at this in the last session. We did one question from the worksheet, which was question number 11, which was quite straightforward. Then we looked at question number 8, but we were not able to complete it in the last session. I'll quickly complete it. There was a careless error at the end as well, and my iPad's battery also ended. So let's quickly complete this question. Then you can let me know what problems you have from the worksheet. In fact, you can write the problems that you have in the chat box already, so we can start working on them right away after doing this question. Let me complete this before we move on. So we had this scenario, this situation that we had two particles, P and Q. They were moving on this smooth inclined plane. They started from the same instant. One was moving downwards and the other was moving upwards. The initial velocity was 1.3. In the first part, we showed that the distance between the two particles was given by 2.6 times t, right? Where t represents the time after they started moving. When t equals 2.5, now it says the difference in the vertical height of the particles is 1.6. So we basically viewed a diagram like this, that, okay, after 2.5 seconds, it's a situation like this, that the distance between, no, the vertical height between the particles, that is 1.6 meters. The difference between vertical heights, that is 1.6 meters. We need to find the acceleration of the particles down the plane. How do you find acceleration? Acceleration for this smooth inclined surface where weight is the only force acting is going to be given by 10 sine theta, right? Acceleration is found using 10 sine theta when you have weight as the only force on an inclined surface. Now, the only problem is we don't know what the value of theta is, right? So for that, we said we could use trigonometry. If we could somehow find this length, we found this length because from the first part, we knew that the distance between the two particles was given by 2.6 times t. We input the value of t, 2.5, in this equation, and that gave us that the distance between the two particles should be 6.5. So that means this hypotenuse is 6.5. This perpendicular is 1.6. What's the ratio between perpendicular and hypotenuse? It's sine, right? So we say sine of theta, that equals 1.6 divided by 6.5. Now, in fact, in acceleration formula, we just need to input sine theta. We don't even need to calculate theta now. We just input this directly there. And we can say acceleration is given by 10 sine theta, right? What's the value of sine theta? This is sine theta. Just input this directly here. Instead of calculating the angle first and then finding sine again, you can just directly input 1.6 over 6.5 here. And that will give you the acceleration value. What does the acceleration that turn out to be here? What's the acceleration? Anyone?
0.04296. Oh, no, I put the value wrong. Wait.
It should be greater than 1 because this is, yeah, can't be 0 point something. I think I should have my calculator with me as well.
So
To speed up
2.46.
the process. 2.46. Okay. Acceleration is 2.46. 2.46 meters per second square. That's the acceleration that we get. That's what we have to find in this part. Okay, now in the next part it says, find the distance traveled by P when Q is at its highest point. Distance traveled by P when Q is at its highest point. So in fact, we should be using a more accurate value here because now we might need to use acceleration in the next part. And you're telling me acceleration is 2.4615. Okay, let's actually use a more accurate value, right? So that our final answer turns out to be more accurate. You can write it down to 3 significant figures at the end, but have the more accurate number written down there as well in case you need to use that for the next part. So the more accurate number is 4615. Okay, so that's the acceleration. Now, in the next part, now we are given, now we have to find the distance traveled by P when Q is at its highest point. Okay, so we have this situation, we have these two particles. Now what happens is, Q was moving upwards and P was moving downwards. We know the angle of inclination of the plane now as well, or at least the acceleration. Let me actually copy that first diagram instead. This is what the situation looked like. P was moving downwards, Q was moving upwards. At some point, when Q is moving upwards, when it reaches its maximum height, its velocity is going to become 0. We need to find the distance traveled by P until that point. Okay. Now Q is moving upwards, P is moving downwards. At some point, Q comes to instantaneous rest. We can first find the time taken until that point for Q, and then use that time to find the distance traveled by P during that time. Now, what information do we have about Q and P? Let's write that down here. For Q and P, P is moving downwards, so we're taking that direction as positive for that. Q is moving upwards, we're taking that direction as positive for that. Initial velocity for Q was 1.3. We also know acceleration now. Since we are taking up the plane positive for this, acceleration is going to be negative. So that's minus 2.4615, right? What else do we know? Final velocity. Final velocity is supposed to be 0. How much time does it take? We can use V equals U plus 80 for this. V equals U plus 80. And that's going to give us the value of T here. What's the value of T? 0 equals 1.3 minus 2.4615 times T. What's the value of T that we get? What's the value of T that we get?
0.528.
0.528. Okay, again, it's better to use more accuracy here. 528. What's after that?
133.
528, 133. Because it's not the final answer. If you're already rounded off to 3 significant figures, your final answer might not be accurate, and you might lose one accuracy mark for that. So you have to be careful about it. Okay, so this is what we get. Now, let's put this in the other equation. What do we know about P? Initial velocity for P was 1.3 as well. Acceleration is going to be positive for P because we're considering the downward direction positive. Acceleration is also downwards. So acceleration is 2.4615. We need to find displacement. Now we know the time taken. Time taken is 0.5281. Displacement is what we need to find out. We can use this formula for that. S equals ut plus half at squared. Just input values in that. 1.3 into 0.5281 2.5281 plus 1/2 into A, which is 2.4615 into 0.5281 squared. And that's going to give you the distance traveled by P until Q reaches its maximum height. Okay, what's this value?
One 1.0297.
1.0297. So now it's the final result. This is something that we can round up to three significant figures. Now we would say this is 1.03. All right. So the final result is 1.03. That is what we were looking for. That's our final answer. Okay. I hope that makes sense. Now let's look at a few more questions today. So today and tomorrow, we just want to do some practice questions. So let me know what problems you have from the worksheet so we can start with them. I hope you had the chance to attempt some of those questions.
So question 26 and question number 2 both are pretty much the same. So can you do like any one of them? They had some parts where they had friction between the boxes used to define acceleration of the boxes, the limiting acceleration of the boxes.
Yeah, so we will look at this boxes question. We'll look at that towards the end of today's class. That's a slightly more complicated one. Before that, I want to do any other problems that you have first. Any other problems apart from that?
So question 22's last part.
Okay, let's start with this one then. 22. 22. Okay, let's try this. Question number 22 from the worksheet. A particle moves up a line of greatest slope of a rough plane inclined at an angle alpha to the horizontal, where cos alpha is 0.96 and sine alpha is 0.28. So we have this inclined plane. The angle of inclination of the plane is alpha. We are given cos alpha and sine alpha. We are given that the normal component of the contact force acting on the particle has magnitude 1.2 Newton. Given that, we need to find the mass of the particle. Now, the particle is moving up the plane. Okay, the particle is moving up the plane. Now, let's look at the forces that are acting on this particle. So let's say the particle is here. It says the normal component has magnitude 1.2 Newton, so that means this reaction is 1.2. It's a rough plane, that means there's going to be friction as well. The particle is moving up the plane. Since it's moving up the plane, where is friction going to act? It's going to act down the plane. This is the direction of friction. What other forces do we have? We have weight of the object, weight of the particle. Where does weight act? Vertically downwards. That's the direction of weight. Vertically downwards. What else? Do we have any other forces? Do we have any other forces acting on the block? Acting on the particle? Any other forces acting on the particle?
So friction force.
Yeah, friction is already represented here. This is friction. Anything that we have not represented? Is there going to be a force acting up the plane? How is the particle moving up the plane? Should there be a force in this direction?
Yes, sir.
Yes. Are we going to
Yes.
assume that? Should we take that assumption? Or should we not?
We shouldn't, sir.
Well, you just said you should, and we should, and now you're saying not.
So
We
there is
shouldn't.
a force, but we shouldn't assume it because they haven't given us any details about the force acting.
So you're saying there is a force, but we should not use that. How would that make sense? So that means there's a force that we're ignoring. How can we do that? We should consider that. We could, if there is a force, then we should consider that to be something. Let's call that P, and then we might have to find the value of P as well. But is there a force at all? They have not mentioned there is a force. You're not going to assume there is a force. The reason for that is it is possible for the particle to still move upwards even without a force acting in the upward direction. How? I think I've given this example before as well. Think of yourself throwing a ball upwards in the air, right? When you throw a ball upwards, when you release the ball from your hand, it still keeps going up for a while. Now you're not going along with the ball. You're not applying any force with the ball after you've released it, but the ball still keeps moving upwards for a few seconds, right? Why does it still keep moving upwards? Because it has some velocity. It doesn't come to rest instantaneously. Because of that initial push that you've given it, it keeps moving up for a few seconds. And then after that, it comes back downwards. All right. So even without a force, if the object already has some velocity, it will keep moving in that direction. So in this case as well, you can think of this as a case where the particle is kind of projected from the bottom of the plane, or think of it as a ball that you're rolling from the bottom of the plane. You've rolled it up the plane. Now, after you've released the ball, it will still keep moving upwards for a while until its speed becomes zero and then it starts coming back down. Does that make sense?
Yes, sir.
So there's no force acting on the particle in the upwards direction at this point. All right, there's no force. You're not going to assume that. Okay. Now, I'm just connecting my other device again. Disconnected. Okay. All right, so these are the forces that are acting then. We're not going to assume there's a force acting up the plane because it's not given. We're not going to assume it. We have to find the mass of the particle. Now, the particle is moving along the slope, along the plane. There's no movement perpendicular to the plane. And in fact, there will never be a movement like this in your syllabus. Projectile motion is not part of your syllabus. So when the particle is moving along the plane, it's only moving in this direction. Now, if it's moving along the plane, what that means is the forces perpendicular to the plane, they are always going to be equal to each other. Remember the directions that we used to consider in case of an inclined plane? We would say, considering yourself standing on the plane, what's the upward direction? This is the upward direction. This is the downward direction. This is right. And this is left. When an object is moving along a plane, upwards and downward forces, they are always going to be equal, because in our syllabus, there can't be vertical movement, like perpendicular movement to the plane like this. So all we have to do is just equate these forces. How do you do that? Weight will need to be resolved. First of all, weight is acting vertically downwards. What are the components of weight? If this angle is alpha, we can say this angle is also alpha. So we have one component here, which is W cos alpha, and the other component here, that's going to be W sine alpha. So these are all the forces acting on the particle. We've resolved them, W cos alpha and W sine alpha. Now, since these forces are supposed to be equal, we say W cos alpha should equal, the upwards force should equal the downward forces. That means R should equal W cos alpha. The value of R is 1.2. W could be, since we're looking for mass of the particle, we could say W is 10 times m. What about cos alpha? Cos alpha is 0.96. We could use this information to find the value of m. You can see what that turns out to be. What's m?
0.125.
0.125. That is the value of m, 0.125 kilograms. Okay, that's the first part. We just had to equate these opposite forces, R and W cos alpha. Let's look at the second part. Now it says, given that the frictional component of the contact force acting on the particle, that means friction, has magnitude 0.4 Newton. So now they've also told us that friction is 0.4 Newton. This is 0.4 Newton. So while the object is moving, while the particle is moving, the friction between the particle and the surface is 0.4 Newton. Okay, that's given. Find the deceleration of the particle. Now we're talking about forces and we're talking about deceleration, that's acceleration, right? It'll just turn out to be negative. How do you find deceleration of a particle? You can use Newton's second law of motion, right? So how do you use Newton's second law of motion for that now? You will need to consider the forces that are acting. In which direction is the particle moving? The particle is moving up the plane. So we're considering up the plane positive. That's the direction of motion, right? We can say resultant force equals mass into acceleration. What's the forward force? What's the forward force? In the direction of motion, there's no forward force. We can say 0, or we can just not write anything there. What are the backward forces? 0.4, that's friction, and W sine alpha. This should equal mass, which is 0.125, times acceleration, which is what you have to find out. So we have minus 0.4 minus W. What was W? 10 times m. So that's 1.25, right? 1.25, that will be the value of W. Into sine alpha. Sine alpha is 0.28, that's given in the question. That equals 0.125 times A, and that is going to give you the value for acceleration. What do you get from this?
6 meters per second square.
6 meters per second square. That is the acceleration that we were looking for. Okay, that was the second part of this question. Now let's look at the next one. Now it says the particle comes to rest on reaching the point X. So there's some point X that this particle reaches, and at that point, this particle comes to rest. Now, what does that mean? They're basically talking about instantaneous rest. You see, the particle is moving upwards. There's deceleration. That means there is negative acceleration. The speed of the particle is going to keep reducing, and at some point, it's going to reach its maximum height. Maybe that's this point, and then it's going to start coming downwards, or try to come downwards. Okay, because it can't go towards the right anymore, up the plane anymore. It comes to instantaneous rest. Now, when it comes to instantaneous rest, they're basically asking us whether it starts moving down the plane after that, or it just stops there. Now, looking at this diagram, it's an inclined surface. It looks like it should start moving down the plane. However, remember, it's a rough surface. It's a rough surface. That means there's going to be friction as well. That is going to stop this object from moving. So we need to figure out, is friction enough to be able to stop this particle from moving, or is it not? Let's try to figure that out. Part 3. So now what happens is, this particle keeps moving up the plane until it reaches this point X, at which its velocity becomes 0, right? So let's say it has reached this point X. Now what happens is, it starts or tries to start moving downwards because of the weight, right? What are the forces acting on this particle? You have weight. The component of weight acting in this direction is W sine alpha. sorry, W cos alpha, which was W was 1.25. So this is 1.25 cos alpha. And we have reaction. Reaction was 1.2. We had W sine alpha acting in this direction. Now, when the particle comes to rest at that particular point, in which direction is it going to start trying to move now? There's component of weight that is acting down the plane. That component of weight that's acting down the plane, it's going to try and make the object move downwards, slide downwards. Friction is going to oppose that. In the previous case, the particle was moving up the plane, so friction was acting downwards. Now, when the particle comes to instantaneous rest, because of the weight of the particle, it's going to start trying to come down the plane now, slide down the plane now. Where is friction going to act? Friction is going to oppose that possible motion, and it's going to act in this direction. That's the direction of friction. Now, if W sine alpha is greater than friction, the object is going to move down. If it cannot counter friction, the object is going to stay there. So we basically need to figure out whether W sine alpha can counter friction or not. What's the maximum value of friction? Do we know what the maximum value of friction is?
0.4.
F max is given by mu r. We don't have any coefficient of friction here. How do you know it's 0.4?
So we don't because they've given it, we don't particularly need the maximum force because the downward force by the W sine theta force in itself is 0.35 and 0.4 we already aware that 0.4 is a greater force.
So does that mean because of 0.4 acting up the plane and 0.35 acting down the plane, the particle is going to move upwards?
No, so that's friction force. Since it only opposes the force which is being applied, it won't go further. It will just remain at rest.
Yeah, so that's very good. So basically, we have two forces. We have one force W sine alpha, and the other force is friction. Now, what is the maximum possible value of friction? Remember, we discussed this in forces in equilibrium. When we talked about friction, we said friction is going to be at its maximum value when you have limiting equilibrium or when the object is in motion. In these two cases, friction is going to be at its maximum value. Now, they're basically given us, while the particle was moving up the plane, the friction was 0.4 Newton. Now, when the particle is moving, the friction is supposed to be at its maximum value. So that basically tells us that the maximum possible value of friction, F max, what is that? That is supposed to be 0.4 Newton. The maximum possible value of friction is 0.4 Newton. And what about W sine alpha? W is 1.25. Sine alpha is 0.28. What does that turn out to be? You're telling me this is 0.35. So we have 0.35 here as the value of W sine alpha. 0.4 is the maximum possible value of friction. Now, since the downward force that is acting, the force that's acting down the plane is less than the maximum possible friction, that means the object cannot slide downwards because friction is going to stop it from moving. If you have 0.35 acting down the plane, friction is also going to be 0.35 and it's going to stop the object from moving because the maximum possible value of friction is 0.4. So even if this downward force was 0.37, friction will become 0.37 and not let the object move. If the downward force was 4, friction was 0.4, friction would also become 0.4 and the object will still not move. However, if the downward force was, for instance, 0.41, now since it's greater than the maximum possible value of friction, the object will start moving downwards. In this case, we have figured out that W sine alpha is 0.35. That means the downward force acting is 0.35. The maximum possible value of friction is greater than 0.35. that means the object is going to remain at rest, right? So that's what we have figured out. We have figured out that W sine alpha is less than the maximum possible value of friction. And that means the particle cannot slide downwards. It will remain at rest. Is that okay? Make sense?
Yes, sir.
Okay, any other questions from the worksheet? Apart from 2 and 26? Let's do one more question apart from that, and then we do one of those. Other problems? Anyone? Have you attempted the questions that I asked you to do, all of them? $51? Okay. 51. How much time do we have? Okay, let's try this. Question number 51, and then we'll do one of those 2 and 26, and then we end for today. In the next class, we will do a couple of more questions. I will actually tell you a few more questions to attempt. You should attempt those 2 specific questions that I asked you to do apart from the worksheet, in addition to these questions. And in the next class, Thursday, or in fact Friday, will be the last one that we spend on this topic. On Saturday, we will start work, energy, and power, inshallah. And we might actually complete the concept of work, energy, and power on Saturday as well, so that you can attempt the questions before Tuesday then, because that's not a very big topic either. We will be able to complete the concepts, and then it's more about practice. And then it's the same with momentum as well. That's also a very short topic. But work, energy, power will take time in terms of practice, because it does have some tricky questions. Let's have a look at this. Question number 51 from the worksheet. So it says particles A and B have masses 0.32 kilograms and 0.48 kilograms respectively. The particles are attached to the ends of a light insensible string. Okay, so let's highlight the information that's not given there. 0.32 kg and 0.48 kg. It's not shown in the diagram. These are the masses of the particles. You have a string passing over a pulley. It's a smooth table, so there's no friction. Okay, this is shown in the diagram. The height is also shown in the diagram. B is released and A moves downwards. Okay, so the rest of the information is there in the diagram as well. We need to find the acceleration of A and the tension of the string. Okay, so that's a pretty standard Newton's second law of motion question. We have 2 particles that are connected to each other. We need to find the tension and acceleration. You'll find this in every other question that involves Newton's second law of motion. You have connected particles, and you just have to apply Newton's second law of motion on each of them separately. Let's do that here. So we have 2 particles. One is A and the other is B. Let's look at the forces acting on both of these particles one by one. So let's start with A first of all. We have the weight of A. Where does that act? Vertically downwards. That's going to be 0.32 kg. That's 3.2 Newton. That's the weight of the object acting downwards. Weight of B is 4.8 Newton. What other forces acting on A? Tension. Away from A, that's in the upward direction. And that's it. On A, we don't have any other forces acting. What about B? At B, we have reaction. Although we don't really need that because there's no friction. Generally, we need reaction when we have to find friction using F equals mu r. But we don't need that here. But we have reaction acting upwards. Okay, we just represent that. That's one of the forces acting. What else? Is there any force acting towards the right side? No. There's a force acting towards the left side, that is tension. Since the surface is smooth, the table is smooth, there's no friction. These are the only forces acting on the particle B. Right? That's pretty much it that we have. Yeah. Now, let's just apply Newton's second law of motion on each of those particles one by one. It looks quite straightforward, actually. The first part, A is moving downwards. So we say the downward direction should be positive for that. B is moving towards the left side. So we're saying left is positive for B. Just apply Newton's second law of motion on each of them separately. Forward force minus the backward force, that equals mass into acceleration. What's the forward force for A? It's moving downwards. The forward force is 3.2. So we say 3.2 minus tension that was acting upwards, backward force, equals mass of A, mass is 0.32, times acceleration. Do the same thing for B. B is moving towards the left side. Now, since it's moving towards the left side, and we're saying the left side is positive, what's the forward force? The forward force is T. What about the backward force? There's no force opposing the motion of this object. So we say the backward force is just 0. So we can say T minus 0 is equal to mass of B, which is 0.48, times acceleration. We have these two equations. All we have to do is solve these two equations simultaneously, and that is going to give us the value of T and the value of A. That's all that we have to do in the first part. Now, what we can do is we can make T the subject here. In fact, it's already the subject. T equals 0.48 times A. You can input this in the first equation, and that will give you 3.2 minus 0.48 times A. That equals 0.32 A. 0.48 goes to the other side, and that gives you 0.8 times A. That equals 3.2. The value of A turns out to be 3.2 divided by 0.8, which is 4 meters per second square. That's the acceleration. You put this back in the other equation. That gives you T equals 0.48 times 4. And that turns out to be 0.48 into 4. That's 1.92 Newton. That's what we were looking for. We have the acceleration and tension. That's the first part, right? Now it says A hits the floor and B continues to move towards the pulley. Find the time taken from the instant that B is released for A to reach the floor. Okay. Now A is moving downwards, B is moving towards left. What's the time taken for A to reach the floor from the instant that B is released? So basically, when the particle, after the particles start moving, how much time does A take to reach the floor? Well, A is moving downwards. We can take downward direction as positive for A. We have pretty much all the information that we need for this. Downward direction is positive, right? Because it's moving downwards. What's the initial velocity? It started from rest, right? Initial velocity is 0. We have found the acceleration in the previous part. That's 4 meters per second square. So we can say acceleration is 4. What else do we know? We know the displacement, 0.98, right? The displacement until the floor is going to be 0.98 meters. So that's 0.98. What we want to find is the time taken. So T is what we have to find out. What equation connects? Which equation connects these four things? S, U, A, and T. That's S equals UT plus half AT squared. S equals UT plus half AT squared. Just input values in this. That will give you the value of T. S is 0.98. That equals U, which is 0 times T, plus half into A, which is 4 into T squared. And that gives you 2T squared equals 0.98. T squared equals 0.49. And then square root of that, 0.7. Yeah, so I think that should be 0.7. T equals 0.7. Generally, whenever you take square root, you put plus minus, but in this case, since we're talking about time, it can only be positive. So time equals 0.7. Okay, so that's the second part. This is the time taken for A to reach the floor. Okay. Now let's consider the third part. Now it says find the time taken for B to reach the pulley. Now B is moving towards the left side. At some point, it's going to reach the pulley. How much distance does it have to travel for that? 1.4 meters. Okay. So it's going to take 1.4 meters for B to go towards the left side and reach the pulley. How much time does it take for B to reach the pulley? Now think about it. When A hits the floor, the string is no longer going to be taut. Remember the difference between a taut string and a string that is slack. A string that is taut means it's the string is straight, basically, right? That means there's going to be friction. There's going to be tension in that string. When the string is slack, it looks like this, for instance, right? It's not straight. So if you have two particles connected like this, there's a block here, and it's connected to another particle using a string like this. Now, if the string is in this position, such that it's not straight, its parts are not straight, these objects are not going to be applying any forces on each other, right? The force can only act when this string is straight, when the string is taut. Now, once you have that sorted out, once you understand that, you will understand that you'll have to break this journey into two parts. One part is while A and B are connected by the string and the string is taut. So what happens is after some time, we found that time already in the first part. In the second part, in fact, A is going to hit the ground. A is going to come down. It's going to hit the ground. How much time does that take? It takes 0.7 seconds. After 0.7 seconds, A will hit the ground. Now, in those 0.7 seconds, B is going to come somewhere here as well, so that this distance is 0.98 meters as well. Okay, this is the part of the string. This is the part of the motion while the string is taut. So we are basically going to break our journey down into multiple parts like this. Now, this is something that will be very helpful in some of the other questions that we'll do later as well. Whenever you have multiple parts of a journey, I would suggest that you label those parts on your diagram like this so you can refer to them when you're working. For example, we could say the point where B started from, let's call that point X. And then at some point, the string is going to become slack. Let's call that point Y. And then the particle B is going to reach the pulley. Let's call this point Z. So from X to Y, the string is taut. When B reaches Y, A is going to hit the ground. When A hits the ground, the string is no longer going to be taut. The string is going to be slack. So from Y to Z, the string is going to be slack. So we have two parts of this journey. One from X to Y, and then from Y to Z. We will have to consider those two parts separately. X to Y, that's one part of the journey. And Y to Z, that's the other part of the journey. In X to Y part, the string is taut. Now, once you label those points like that in the diagram, it's going to make your working easier. I can just refer to those points like this. It'll help you in your calculation as well. You'll understand exactly what you're doing once you write it down like this. So from X to Y, the string is taut. From Y to Z, the string is slack. We need to find the total time taken from X to Z. Now we already know from X to Y, the time taken is 0.7. We already know that time. The problem is we need to find the time taken from Y to Z. And that's the next part of the journey. Now, if the displacement in the first part of the journey was 0.98, the total is 1.4. What is left here? 1.4 minus 0.98, that's 0.42 meters. So from Y to Z, we know that displacement is 0.42. Okay. What we need to find out is the time taken. What else do we know? Do we have the initial velocity, the velocity at y? Well, we don't. For yz part, we don't know what the initial velocity is right now. Okay, do we know the final velocity? No. Do we know acceleration? No, acceleration is no longer going to be the same as before because 4 meters per second square was acceleration when the string was taut. When the string is no longer taut, the acceleration is not going to be 4 meters per second square anymore. It's going to be something else. So now for the second part of the journey, we only have this information for now, s equals 0.42. Now notice, for the first part of the journey, y is the end point. And what do we know about the part of the journey from x to y? We know the time taken. We know acceleration. Acceleration was 4 meters per second square. We also know displacement. Displacement was 0.98. And we also know the initial velocity. The particle started from rest. So we have all of this information. What we can do is we can find the final velocity from the first part of the journey. So we can find the value of v from this. V equals u plus at. Let's use that and see what that gives you. 0 plus 4 times 0.7, and that's going to be 2.8 meters per second. This is the velocity of the particle at the point y. Now, if the velocity of the particle at point y is 2.8 meters per second, the second part of the journey is from y to z. So that means the initial velocity from y to z, that is going to be 2.8 meters per second as well. Okay. Now we need to find the time taken for this part of the journey. We do not know displacement. In fact, we do know displacement. We don't know final velocity and we don't know acceleration. Can we say anything about acceleration and final velocity for y to z part of the journey? Can we say anything about acceleration from y to z? Any idea? What forces are acting on the particle from y to z?
So the final velocity can be zero because there would be no more tension in the string as well.
You're saying the velocity of particle b when it reaches pulley should be zero?
Yes. The final velocity.
Why?
Because it's
How
not
can you?
moving, it's not, it's coming to rest, although they have not mentioned, but it's not moving down. They have not asked about that.
No, but we are basically supposed to find the time taken until it reaches the pulley. Now, how do we know it reaches, when it reaches the pulley, its velocity becomes zero? What if its velocity was greater than zero? It just hits the pulley at some point. We don't know whether it comes to rest at that point or not. Can't be sure about that. Can't assume it. It could reach the pulley at a speed that is greater than zero as well. What are the forces acting from y to z? Do we have any forces acting from y to z in this part of the journey? There was tension acting earlier. Now there's no tension. There's no other force, there's no friction. So basically, there's no force acting. From y to z, there is no force acting on the object. If there's no forces acting, the object is going to keep moving at the same velocity, at the same speed. Its speed is going to be constant. It's not going to change. Why? Because if there are no forces, we can say resultant force equals mass into acceleration. If resultant force is zero, that means acceleration is zero. Right? If resultant force is zero, acceleration is zero. And if acceleration is zero, the velocity is going to be constant. So from y to z, acceleration is going to be zero because there are no forces acting on the object. And if acceleration is zero, what that means is whatever the velocity was initially, the particle is just going to keep moving at that same velocity. So v should be also 2.8. its velocity is not going to change at all. Okay. And what do you need to find out now? Time taken. You can use v equals u plus at. In fact, this is constant velocity. You could also just use speed equals distance over time, or time equals distance over speed. That will also work in this case, but you can just use these formulas, constant acceleration formula. Zero is also constant. So just use this 2.8 equals 2.8 plus a, which is zero, times t. Okay, sorry, this is not going to help because time is going to get eliminated. So we need to use some other equation. What other equation can we use? S equals ut plus half at square. You could use that. What does that give you? S is 0.42, U is 2.8 into T plus half into A, which is 0, into T squared. And T equals 0.42 divided by 2.8. That's giving me 0.15. 0.15 seconds. So the first part of the journey took 0.7 seconds. The second part of the journey took 0.15 seconds. So what's the total time taken for B to reach the pulley? It's 0.7 plus 0.15, which is 0.85 seconds. That's the total time taken for B to reach the pulley. Does that make sense?
Yes, sir.
Okay. Marina, is that okay? Okay, good. No questions on this? Okay, so the no questions, let's look at one last question then, and then we end for today. So we have these questions in which you have one box on top of another box. So we have question number 26, and there's another question that's very similar to this. That's question number 2. Now in this one, you have 3 different parts of 3 marks. Question number 2, you have 2 and 7. Okay, so this is maybe slightly more tricky because there's one part of 7 marks that you have to figure out yourself. Let's do this one. Once you understand this, you should be able to do the other one as well. That's going to be almost exactly the same method. So let's do this. Question number 2 from the worksheet. And using that, then you can do question number 26 as well. Okay, question number 2 from the worksheet. Just give me a minute. I'm going to leave a message on another group. Okay. So we have these 2 boxes, 2 identical boxes, each of mass 400 kg. They are at rest, with one on top of the other. They are on horizontal ground. So both of them have masses 400 kilograms. A horizontal force of P newtons is applied to the lower box. You can see that in the diagram. It's acting towards the left side. We can represent this force on the left side here, like this. This is the force acting towards the left, P Newton. The coefficient of friction between the lower box and the ground is 0.75. And the coefficient of friction between the 2 boxes is 0.4. So there's going to be friction between the lower box and the ground, and also friction between the 2 boxes that we've learned. Show that the boxes will remain at rest if P is less than or equal to 6,000. Okay. Remain at rest, what does that mean? That means they're going to remain in equilibrium. right? And you have to prove this, that P is less than or equal to 6,000. Now, first of all, let's represent all the forces that are acting on these two blocks. Now, in fact, we just have to consider the two boxes together for now. So let's consider the forces acting on the lower box and the ground. One is the force acting towards the left side, P Newton. I'm just going to erase it from the right side because it's acting towards the left side. It's often helpful to just represent it on the side at which it's acting and the direction at which it's acting. What are the other forces acting? 400 kg is the mass of the blocks. Of each of the blocks, the mass is 400 kg. The total weight acting downwards at this point, what is that going to be? 400 plus 400, the total mass of the two boxes is 800 kilograms. The total weight that's going to be acting downwards is going to be 8,000 Newton. That's the total force acting on the ground at this point. And what about the reaction? The ground is going to give you a reaction for this. That is also going to be the same. The reaction is also going to be 8,000 Newton in this case. There's weight of the block, weight of the two blocks, and this reaction. The reaction is also 8,000 Newton. What other forces do we have? If there's P Newton force acting towards the left side, that means this force is trying to make the object move towards the left side. There's going to be friction acting opposite to that to try to stop it from moving. So there's friction acting towards the right in this case. These are all the forces that are acting on the lower box. Okay. Now, since the boxes are supposed to remain at rest, when will they remain at rest? If P was too big, the objects will start moving towards the left side. What's the maximum possible value of P that we can have? One idea is that you consider the limiting equilibrium case, considering that the boxes are just about to move towards the left side. Consider that extreme case, the limit of equilibrium. Consider the case that the objects are just about to move towards the left side. That will give you the maximum possible value of P. If the maximum possible value of P turns out to be 6,000, you could say P is supposed to be less than equal to 6,000 if the objects are supposed to remain at rest. That's one possibility. So you can consider the case of limiting equilibrium. Consider limiting equilibrium with the object just about to move towards the left side. And just write that down directly. If the objects are just about to move towards the left side, what are the opposite forces acting? P is equal to F and R is equal to 8,000. Now, if it's limiting equilibrium, friction is going to be equal to mu R. What's the value of mu? Friction between coefficient friction between the lower box and the ground, that's 0.75. So we say P equals 0.75 into R, that's 8,000. P turns out to be equal to 6,000 Newton. This is the maximum possible value of P. Maximum possible value of P for which the blocks will remain in equilibrium. Why? Because we are considering limiting equilibrium. When the equilibrium is at its limit, that the object is just about to move towards the left side. If P was slightly bigger than this, the object will start moving. So for that reason, we can say P is supposed to be less than 6,000 Newton. If the maximum value is 6,000, that means P is less than or equal to 6,000 Newton. That's one way of thinking about this. Another possibility could be, since you know that the objects will remain at rest, that means it's equilibrium. We don't actually know if it's limiting equilibrium or non-limiting equilibrium. Remember that case that we did in friction? When we do not know whether the equilibrium is limiting or non-limiting, we used to say F is less than or equal to mu R, right? We've done this in forces in equilibrium. We use this to prove inequalities in that topic as well. You could use that concept and you could say, again, it's equilibrium. Opposite forces are supposed to be equal. So you have P equals F and you have are equal to 8,000 Newton. That is still going to hold. However, now we can say friction is supposed to be less than or equal to mu r. Why? Because we are in equilibrium. And we do not know whether this equilibrium is limiting or non-limiting. We can just input values here. Friction is P, that's less than or equal to mu, which is 0.75 into R, that's 8,000. So from this, we could get directly that P is less than or equal to 6,000 Newton. That could be another way of thinking about this. You could get that inequality from this directly. Does that make sense? Any problem with this?
No, sir.
No? Okay, now we're running out of time, so I'm going to be a bit quick about the second part now. I would ideally want to ask you first, or let's actually spend a few minutes on this to try to understand this better. So now it says in the second part, the boxes start to move with acceleration A. So now the boxes start to move towards the left side, right? The force is acting towards the left side, so the boxes start moving towards the left side. And they start moving at an acceleration of A meters per second square. And now it says, given that no sliding takes place between the boxes, show that A is less than or equal to 4, and then deduce the maximum possible value of P. Now we need to think about this a little. It says, given that no sliding takes place, show that A, the acceleration is supposed to be less than or equal to 4. Now, basically what happens is the force that is acting here, the force P, that is acting on the lower box, right? The force is acting on the lower box towards the left side. Now, if that force was too big, think of this scenario that let's say you have two matchboxes, right? They're pretty light in weight. So that will probably help you understand this better. Let's say you have two matchboxes, one on top of the other. If you were to apply a force on the lower matchbox, and if you were to apply a significant amount of force quickly on the lower box, imagine what would happen. Try to visualize what would happen. The lower box is going to move forward, and the upper matchbox is going to slide down, right? Where will it slide down? So the lower box will move towards the left. The upper box will slide down on the floor, right? If you were to apply too much force on the lower box. On the other hand, if you were to apply just a small amount of force on the lower box, both the matchboxes will move together, as in you will only be applying a force on the lower matchbox. The upper matchbox will keep moving along with that if the force applied is not too much. So if the speed of motion is not that high, there's going to be no sliding that takes place. But if you push the lower box too hard, the upper box is going to slide down and fall. So in this case, what they're basically saying, if no sliding takes place, you need to show that acceleration is less than or equal to 4, which means if acceleration was greater than this, if acceleration was, let's say, 10 meters per second square, what would happen would be the upper box would slide and fall down. Okay. For no sliding to take place, the acceleration at maximum can have a value of 4. It cannot be greater than 4. If it's greater than 4, there will be sliding that takes place. That's what this statement means. That given that no sliding takes place, show that acceleration value is less than or equal to 4. Okay. Now that we have that sorted out, let's think about the forces acting on the upper box now. What are the forces acting on the upper box? When the force is applied to the left side, why does the upper box start moving? Let's try to think about that. On the upper box, first of all, we have the weight of the object acting, weight of the box acting. In which direction is that weight going to act? Downward direction. What's that weight? 4,000 Newton, right? The upper box is going to be applying a force of 4,000 Newton on the lower box. And the lower box is going to give you a reaction for that. It's going to give the upper box a reaction for that, which is going to be 4,000 Newton as well. So in the upper box, there's going to be a reaction of 4,000 Newton. Okay. What other forces are there? There's going to be friction between the two boxes. In which direction is friction going to act? What do you think, quickly? Where is friction going to act? On the upper box. Backwards? In which direction? What backwards? What is that? Right or left?
Side. Right side.
Right side. So you're saying friction is acting towards the right side. Okay. If we say friction is acting towards right side, why is the upper box moving towards the left? What force is making the upper box move towards the left? Why is the upper box moving towards the left? Do we have any force acting towards that? Yes, Salva?
So because of the P force. But the P force is being applied to, so the P force is being applied to the bottom box, and that's causing the friction. So friction would be on the left for the upper one then, which would be equivalent to P.
Yes. So if we consider friction acting towards the right side, that means there's no force acting towards the left side on the upper box. How can the upper box move then? The P Newton force is actually acting on the lower box. There's no force acting towards the upper box in this situation. If friction was to be on the right side, basically what happens is when the lower box has a force of P Newton applied towards the left side, the upper box is going to try and slide down. In which direction is going to try and slide down? Towards the right side. So the upper box is going to try moving towards the right side. It's going to try sliding towards right. Now, to stop it from sliding, friction is going to act in this direction. So the upper box is actually going to move along with the lower box because of the friction between the two boxes. It's the friction between the two boxes that makes the upper box move along with the lower box. So friction on the upper box is actually going to act towards the left side. Is that okay? And it's actually friction that will make the object move towards the left side. Now, why is that? Because this friction is actually stopping the upper box from sliding down. And since it's not sliding down, it keeps moving with the lower box because of that friction. So in this case, friction is what is making the upper box. Okay. Once we have that sorted out, this friction is going to have a limit. If the lower box was pushed by a force that's too big, the acceleration of the lower box is going to be too big. And the friction between these boxes is not going to be able to keep the upper box from sliding. So what we need to do is we need to find the maximum possible acceleration that this friction can basically counter, right? Or what's the maximum possible acceleration that this friction can produce? That is what we need to figure out. Let's first find the maximum possible value of this friction. How do you find the maximum possible value of this friction? So this is the friction between the upper box and the lower box. Let me actually write that down here. So we are talking about the friction acting between the boxes. So what's the friction, the maximum possible value of the friction in the upper box? Let's figure that out. It's mu times r, right? What's mu for the upper box, as in between the two boxes? What's the coefficient of friction for that? It's 0.4. We have 0.4 here. Into reaction, what's the reaction of the upper box? The reaction of the upper box is 4,000. So we have 0.4 into 4,000. The maximum possible friction on the upper box is 0.4 into 4,000, and that is 1,600 Newton. This is the maximum possible friction on the upper box between the two boxes. Okay. If that is the maximum possible friction between the two boxes, now we need to see what is the maximum possible acceleration that this friction can produce. Now, corresponding to this friction, what is the corresponding acceleration, let's figure that out. What's the corresponding acceleration to this value of friction? You can use resultant force equals mass into acceleration for that. For the upper box, what's the forward force? For the upper box, the forward force is this friction, and the maximum value of that is 1600 Newton. If we consider it to be at its maximum value, if we consider the friction to be at its maximum value, what is going to be the corresponding value for acceleration in that case? We can find that like this. Forward force is 1600 Newton, that's Fu. Minus the backward force, that's 0. What's the mass of the upper box? That was 400 into A, and that gives you a value for A, which is 1600 divided by 400, and that gives you 4 meters per second square. So when the friction on the upper box is at its maximum value, the acceleration of the upper box is going to be at its maximum value as well. So this is the maximum possible acceleration that this friction can basically handle. If acceleration was to be any bigger than this friction would also need to be bigger than 1600 Newton. And since that is not possible, if acceleration was more than 4 meters per second square, the upper box is actually going to slide down. And that's what they're saying cannot happen. There's no sliding that takes place, which means the maximum possible value of acceleration is 4. So acceleration is supposed to be less than or equal to 4. That is what we had to prove in the first part of this question. Does that make sense? Any problem with this? Can I have response verbally now? Okay. So between boxes, we get that the maximum possible value of friction could be 1600 Newton. What is the maximum possible value of acceleration that friction can handle? That is 4 meters per second square. That is what we were looking for here. Okay. Now it says, hence deduce the maximum possible value of P. Now, corresponding to this acceleration, what's the maximum possible value of P? Now we could consider this whole system, right? What is the maximum possible value of P that we can have corresponding to this acceleration? Now we could consider the whole system, or you could say the lower box and the ground. Earlier we considered between boxes. Now we could consider the lower box and ground. Let's consider these two now. For the lower box and ground, if the maximum possible value of acceleration is 4, what is the corresponding maximum possible value of P? Let's figure that out. Now, what's the forward force now? For the lower box, it's P Newton. What's the backward force? This friction. Let's apply Newton's second law of motion on this. Forward force is P minus the backward force, that's friction between the lower box and ground. I'm calling that FL. That equals mass. Now remember, on the lower box, both of these masses combined are basically applying force on the ground. So we're going to consider the total mass, that's 800, into acceleration. The acceleration value that you found there was 4 meters per second square. That's the maximum possible value of acceleration. The maximum possible value of acceleration is what is going to give us the maximum possible value of P. Let's use that here, 800 into 4. What does that give you? P max minus friction between the lower box and ground. What's that? since the objects are moving, friction is going to be at its maximum value. We can say that's mu times r. In this case, mu and r are going to be for the lower box now. On the right side, we have 3200. So P max equals mu, P max minus mu, which is 0.75 in the case of lower box, into r. R was 8,000. That equals 3200, and that gives you a maximum possible value of P, which turns out to be 3200 plus 8000 into 0.75, and that's 9200 Newton. So corresponding to that maximum value of acceleration, this is the maximum possible value of P that we have. And that is what we were looking for here. Does that make sense? Any questions on this now? If you have any confusion in this process, let me know, because the second question that you have to do, question number 26, that's almost exactly the same as this. If you understand this, you should be able to do that as well. So now that should be an exercise. You could try that. And if you're able to do that, hopefully you understand this concept. So what you need to remember here is the friction on the upper box is going to be acting towards the left side. Why? Because the object will try to slide towards right. So friction is going to oppose that. That's going to act in this direction. What's the maximum possible value of friction? We found that first. And then corresponding to that, this is the maximum possible value of acceleration that we get. And then we use that maximum possible acceleration to find the maximum possible value of P like this. All right. Any problems, anyone? Any questions on this? Any questions?
So the P max is the value of force which can be maximum applied before the acceleration goes beyond 4, right?
Yes, exactly. So if P was any more than 9200 Newton, acceleration would become more than 4. And if acceleration becomes more than 4, that means the friction between the upper box and the lower box is not going to be able to handle that, and the object is going to slide down. So okay, this is the maximum possible force that keeps the acceleration equal to or less than 4. Okay?
Okay, sir.
Any other questions on this? No? All right, so we'll end this here. In the next class, we will do some more questions. I'll be posting a couple of questions on the WhatsApp group. I would expect you to attempt them before the next class, because those 2 questions in particular, we would want to try, along with any other problems that you have from the worksheet or otherwise. That's what we want to do in the next class, and then we end this topic. If you don't have many questions, we could actually start the next topic in the next class as well, after doing those questions. If not, if you do have questions, we will start the next topic on Saturday then. All right, that's it. I'll see you again in the next class. Allah Hafiz.